Hello everyone. This is part 2 of topic 7, Trigonometric Substitution. Here was our last example where we ended up with, after a trig substitution, the odd power of cosine. A couple things to recall. The main things to make sure we understand is that if you have a sum of two squares under the radical, the radical part's the hypotenuse. If you have a difference between two squares under the radical, then the radical part's the leg. But moreover, if that's the case, the hypotenuse would be the positive term under the radical, the square root of the positive term, of course. One other thing that I added while you weren't looking was the definitions of the 6 trig functions right here in terms of opposites, adjacents, and so on. You know, we use the memory trick, Oscar had a heap of apples, some corn too, or a lot of you like SOHCAHTOA, I know. But we're in particular going to make sure we have to remember that the secant is hypotenuse over adjacent. I kind of assumed the sine and cosine without writing these down last time. But now we'll go to example 2. And in example 2, we see we do have the sum of two squares under a radical. Now remember, you don't care what the actual integrand looks like. You only care what the radical part looks like. And so we claim our a's and our u's as normal. So a squared is 25, u squared is 16x squared. That means that a is 5 and that u is 4x. We do not calculate the du. We immediately go to a right triangle and we claim our reference angle theta. The next thing is crucial. We have to make sure that we label the triangle correctly. And there's 3 parts to the triangle: u, a, and the radical part. And the question I always like to ask first is, does the radical part represent the hypotenuse or one of the legs? And that's dependent on the sign of the two between the two terms that are under the radical. And since it's a sum, the radical part is the hypotenuse. So I'm going to label that right away. And then you could label your u and your a arbitrarily, but I'm going to choose u to be opposite of the angle theta. And there's a reason for that we'll explain in a moment. Now, the 2 major steps, as we saw last time, were labeled as Roman numerals 1 and Roman numeral 2. You do not even think about the trig function that you're about to define here. You always make the ratio in this step of the radical part over the constant. So always radical over a. And then decide what trig function you're dealing with. And the radical part is the hypotenuse, 5 is the adjacent, that's the reciprocal of cosine, which is secant. So that's why I mentioned that moments ago. And then we solve for the radical part. So 5 secant theta is the radical part. Okay, so we're done with that step for now. Now the second major step. You, again, don't even think about the trig function you're about to define. In this step, we always just force the ratio of u over a. So 4x over 5 in this case. Then, with respect to theta, we see it's opposite over adjacent, and that's the tangent of theta. And then we'll solve for x. Easiest way, just multiply by the reciprocal here, so 5/4. So 5/4 tangent theta is our x. But one more step in Roman numeral step 2, and this is one of the most important things to realize, is that in order to satisfy every factor of this integrand, when you get to the point where you solve for x in Roman numeral step 2, you have to calculate the differential dx, because that is always going to be a factor of your algebraic integral. And the derivative of tangent, 5/4 tags along, derivative of tangent, secant squared theta, and tag along the d theta. Okay, so once you go through those two major steps, then you're ready for a complete trigonometric substitution. Because no matter what the integral is made up of, you have every single piece that could possibly be there. The radical part, an x if it's there, a power of x if it's there, and the differential, dx. Okay, I always like to rewrite the original integral. 1 over square root of 25 plus 16x squared dx. Okay, there's not a lot going on here. We just have 1 over, and then the radical part is 5 secant theta. And the only other thing is the differential dx. And that's 5/4 secant squared theta d theta. So notice that this simplifies. We can cancel the 5s. So we'll bring out the 1/4, cancel a factor of secant, and we're left with secant of theta with respect to theta. Okay, that's one of our special integrals. If you look back at the formulas that we've had, the integral of secant we had proven is the natural log of the absolute value of secant theta plus tangent theta. So not one of the basic 6. But then you have to go back and you have to express this final answer in algebraic form. So put back secant theta and tangent theta in terms of their algebraic equivalents, which are actually in Roman numeral steps 1 and 2, but if they weren't there, you could certainly go back to the triangle, because in the triangle you could define any trig function. So we get 1/4 natural log absolute value. Secant was the radical part. Over the constant, and then plus tangent was 4x over 5. Okay, so some of them can be short, but again, these major steps here to lead us to Roman numeral 2 is all that's required, and no matter what the integral was made up of, you will be able to make a complete trigonometric substitution. Okay, this one's a classic. We have something that looks pretty innocent, but it's not integrable by any other method. And if you wanted to try to use a u substitution, it fails because there's no x to satisfy the du. So trig substitution is required. So we're going to start as normal. A squared is 4. U squared 25x squared. Remember, neither are ever negative. The negative is going to dictate how we construct our triangle. Okay, so we get that A is 2, U is 5x. Here's our triangle, reference angle theta. And we have to place the 3 pieces appropriately. Remember, we don't care what's in the integral, we just care about what the radical looks like. And that dictates what A and U are, and it also dictates what the triangle is going to look like. So I always like to fill in the hypotenuse first, and the first question to ask would be, is the radical part the hypotenuse or one of the legs? And because it's a difference between 2 squares, it's a leg, and moreover, the positive term under the radical represents the hypotenuse. And that came from A, so A is the hypotenuse, which is 2. And then you could place the U and the radical part anywhere you want, but I'm going to suggest once again, and this helps to avoid cosecants and cotangents, make the radical part, if it is one of the legs, make it opposite of theta. Okay, so now we're ready for our 2 major steps. First major step, again, don't even think about the trig function you're going to define. Just force the ratio of the radical part over the constant, and then decide what trig function that represents. And the radical is the opposite, constant's the hypotenuse, and that, of course, is the sine of theta. And then we solve for the radical part. So 2 sine theta is this radical part. Okay, second major step. So we're done with that for now. And again, here we're not even going to think about the trig function we're about to define. This step always, we just force the ratio of u over a. In this case, 5x over 2. 5x is adjacent, 2 is the hypotenuse, and that's our cosine function. And we should actually expect that. If you develop sines or cosines in the first step, you better develop cosines or sines in the second step. And similarly, like this last example, we had secants in the first step and tangents in the second step. They go together. If you start mixing secants with sines or cosines and tangents with sines or cosines, you know something's wrong. Because it always should be secant tangent and sine cosine. Not exactly in that order every time, but they go together. Okay, then you solve for x. Get 2/5 cosine theta is x. And somebody might be saying, why do you solve for x? There's no x in there. Well, there's the dx, and the dx is one of the most important factors to consider. So once you get to the point in Roman numeral step 2, where you've solved for x, calculate the differential dx. And the derivative of cosine is minus sine. So minus 2/5 sine of theta. And formally, please pay attention to the fine details, tag along the differential d theta. Okay, so at this point, we're ready to make a change of variables. And we have the integral. So let me say now, we're ready for our trig substitution. I'll recopy the original integral. And making the substitutions, we have radical part from Roman numeral step 1, 2 sine of theta, times from Roman numeral step 2, the differential dx, negative 2/5 sine of theta times the differential d theta. And we'll take time to clean this up. We'll bring the negative 2/5 times the 2, or negative 4/5 out in front of the integral. And then the substance of what's left over is sine times sine, or sine squared of theta with respect to theta. And then we look at that new integral, and this is an even power of sine. So remember, with the even power of sine, or an even power of cosine, this is case 2, where we have to use the power reducing double angle formula. And for sine squared of theta, it was 1/2 times 1 minus cosine of 2 theta. And just in case you encounter it in the homework, if you end up with cosine squared, it's 1/2 times 1 plus cosine of 2 theta. But remember, for an even power of cosine, we have to use these formulas. Okay, so sine squared then, replaced by 1/2 times 1 minus cosine 2 theta. So with respect to theta. Okay, to make the integrations clear, let's separate this into 2 integrals. So minus 4/5 times 1/2 is minus 2/5, so we'll have minus 2/5 integral of 1 with respect to theta, and then plus the 2/5 times the integral of cosine of 2 theta with respect to theta. And each of those are readily integrable. Minus 2/5 integrating 1 with respect to theta, we get theta, so be careful there, make sure you don't write an x. And then plus 2/5 and integrating cosine of 2 theta, that's our linear argument rule. Cosine integrates to be sine, but because of the argument 2 theta, 1/2 sine of 2 theta. And then we'll add our constant of integration. Alright, now I'm going to rewrite this for now, and then there's two major points to make to finish this off. Remember, we said it has to be in algebraic terms, and here we have theta. So if you consider how, you have to consider how are we going to determine what theta is. Well, if you look back at Roman numeral steps 1 or 2, we've defined sine of theta and cosine of theta. And if we have to get at theta, and I'm going to choose to work with the cosine, you could use any trig function you want. I'm going to work with the cosine. If we go up to the cosine, and we know we want theta, then what we have to do is take the inverse. So theta would be the inverse cosine of 5x over 2. Okay, so that's going to take care of that part. And you could have similarly said it's the inverse cosine of, or it's the inverse sine of the radical part over 2. Okay? But to make sure you understand, to get theta, you need to take an inverse trig. And then here, we've got the sine of 2 theta. And there's no linear relationship. Like sine of 2 theta, we're only working with theta. And there's not a linear relationship. What there is, and this is truly what we call the double angle identity, that sine of 2 theta is 2 sine theta cosine theta. So we have to employ that identity. And then we could finally express, we'll recopy the first term, make this plus 2/5, and now we can, sorry, didn't realize you couldn't see that for a second there. Okay, recopy the first term, make this 2/5, and now we could replace sine of theta and cosine of theta by what they were defined to be. And if we look back at Roman numeral steps 1 or 2, or the triangle itself, sine opposite over hypotenuse, so that was the radical part, over the constant, and cosine adjacent, 5x over the constant 2. And then we'll just make this second half look a little prettier. So our final answer, minus 2/5 inverse cosine 5x over 2. Here plus can cancel the 2's. Can actually cancel 5's as well. Let's bring the x out in front with the 2, so plus 1/2 x and the radical part. Okay, so a classic example. Guaranteed you'll see something on the exam that results in a sine squared or a cosine squared. Okay, so we'll stop right there, and got 3 more examples, and I think we should be able to finish that up in a third part, okay? And then that would be the end of this section. So when you're ready, come back and we'll look at part 3 of topic 7, trigonometric substitution.